So here's proof by induction, and there's the learning goals. That's where you should be by the end of this. What I'm actually going to do is cover one type of proof by induction, because it's not actually a topic officially until Unit 3 and 4. I think the textbook's made the right choice and put it in as something that we can cover, but the textbook covers all different types of proof by induction. You're welcome to play with some of them. Today I'm going to cover proof by induction of summation of series, and that'll be the only thing I talk about and give examples on in class. It will be the only work I set from the homework. It will be the only thing that could come up in your exam. And I'll tell you right now, there will be a proof by induction question in your exam that will be summation based. It's a complex procedure, but if you get it right, it'll be an easy question for you. So let's have a look at the idea of proof by induction, or proof by mathematical induction. So I've got two ways I want to talk about it. And the first one is going to be the one in blue. Oh, it's not moving because it's frozen. First one will be the one in blue. This is on your OneNote now, by the way. And that's going to be the Domino Anecdote. I'll probably move on. I'm just going to talk about these. So I'll move on before you can really write them down. But if you wanted to write anything down, I'd write the purple one down. That's the important one. So the Domino Anecdote is this. If you knock down the first domino, you know that every domino will be knocked down in a set of dominoes like this diagram down here. You know that, but you only actually know that because, you know what, I could set this up and I might accidentally separate two of the dominoes too far. And then they don't all fall down. So you only know this, you only know all the dominoes will fall down if you can guarantee that if one domino falls down anywhere, it knocks down the next one. That is actually pretty much proof by induction summarised right there. So if you can show that if one domino falls down, the next one falls down, and then you push the first domino down, then you know that every domino will fall down. That's how this works. And now imagine it for an infinite number of dominoes. And I can guarantee you that of those infinite number of dominoes, they're separated in such a way that the next one will always fall when the previous one falls. Therefore, they will all fall down. So here it is written out here. You plan on knocking down the first domino in an infinite line of dominoes. You assume that the kth domino therefore falls. And if the kth domino falls, that implies the kth plus one domino falls. Therefore, if you knock down the first domino, the second will fall. If you knock down the second domino, the third will fall. The third will fall, the fourth will fall, and so on ad infinitum. So that's the idea. This is what proof by induction comes down to. Here's the purple one, the theoretical. If you can show that something works in the first instance, and when you assume it works in the kth instance, you can prove that it will therefore work in the k plus 1th instance, then you can make the statement it will always work. So if it works in the first instance and you can prove that any instance works implies that the next one works, then the first instance implies the second implies the third implies the fourth, and you can go on like that to infinity. So that is the whole premise of proof by mathematical induction. It is a 4-step process. We'll talk a lot about the 4 steps. The third step is the only one that's actually got any work involved. The first step is 1 or 2 lines showing it works in the first case. The second step is just an assumption. The fourth step is just a summary. The third step, you do some work, and that's it. And that's proof by induction right there. Now I'm going to move on, but I'll give you 30 seconds of silence to ask questions or finish writing down the purple only. Don't write down anything else, otherwise you'll be frustrated when I move on. Now Will's not here today, so should we assume that Will's going to say he's going to watch this video? Everyone want to say hi?
Hi, Will. Hi, Will.
Cool. Hi, Will. I hope you're watching this video. All right, I'm going to shoot down here. Okay, so there's the induction steps. That's pretty much just a summary of the purple ones. And here are some proofs. And just remember, I'm only doing summation proofs with you. So you don't have to worry about any of the other ones in the textbook for your exam coming up. But they will be important in Unit 3 and 4. And therefore, they will be important in the external exam. Almost guaranteed that they will pop up in the external exam. So, induction steps. 1, show it works in the first case. 2, assume it works in the kth case. 3, prove it therefore works in the k plus 1th case. 4, conclude. Every time you'll follow those 4 steps. So let's have a look at example 1, question A. We are required to prove that 2 plus 4 plus 6 plus ... plus 2n is always equal to n times n plus 1. That's what we're trying to prove here. And this is for all n greater than or equal to 1 existing in the natural numbers. Now, I've made a little note in purple here. You might see this question with a summation symbol. This summation symbol means if from k equals 1 to n, the sum of 2k. So at k equals 1 you get 2, at k equals 2 you get 4, at k equals 3 you get 6, all the way up to 2 times n, because it finishes at n, 2 plus 4 plus 6 plus ... plus 2n. So that is basically this, the left-hand side. And that is the other thing that I might just make a note of here. This is called the left-hand side, and this is called the right-hand side. And it is going to allow us to write proofs that are elegant, that don't end with just 0 equals 0 or 7 equals 7. We're going to write elegant proofs where we come down to left side equals right-hand side. So I'll be expecting you to use that notation as we move through as well. So let's go through our steps. Step 1, show for n, for n equals 1. So for n equals 1 I get 2, because that's the first term. And does 2 is the left-hand side? And I should write that the other way around actually. Left-hand side equals 2, right-hand side is equal to 1 times 1 plus 1, which equals 2, which equals the left-hand side. Done. So I've done step 1. I've shown it works in the first instance. That's me knocking down the first domino. Now I'm going to show that if I knock down the kth domino, it will knock down the k plus 1th domino. So step 2, assume for n equals k. So in this case, say that make the statement that 2 plus 4 plus 6 plus ... plus 2k is equal to k times k plus 1. And I'm going to assume that that's true. And so I've written that there. That's now a statement of fact. I'm writing that there now. That is definitely true. And I'm going to use that for step 3. Step 3, prove for n equals k plus 1. So I'm going to start by writing down the thing I'm trying to prove using the previous statement. So I get 2 plus 4 plus 6 plus ... plus 2k plus 2k plus 1. So I've just got an extra 1 there. And over here, instead of k, I get k plus 1. So it becomes k plus 1 times k plus 1 plus 1. There. So I've just taken the k's out, swapped them for k plus 1. Now I need to prove this. So I'm going to do the left-hand side, I'm going to show it equals the right-hand side or vice versa, or maybe they'll meet in the middle somewhere. Typically, with a summation proof, you're going to make a decision based on 2 criteria here for where you start. So here are my 2 criteria. I would be, and some people might start with this side, but I'll be starting with the left-hand side for 2 reasons. 1, it looks the most complex, and the one I can do the most with. But 2, it's got this mystical ... And that's our problem. The ... is the thing we don't know. We have to try and get rid of the ... And that's going to be my goal. And you'll always be able to get rid of it. And I'll show you how now. So I'm going to start with the left-hand side. Left-hand side is equal to 2 plus 4 plus 6 plus ... plus 2k plus 2k plus 1. Now, watch this. Purple bit there is equivalent to the purple bit in my assumption. So I hope you can see that I can take this thing and I can swap it from the assumption with what it's equal to. And that removes a ... And that will happen every time. This is where we'll use our assumption. So the left-hand side now is equal to k times k plus 1 plus 2 times k plus 1. And I can factorise out the k plus 1. Gives me k plus 1, and I'm left with k plus 2. And I could either now get the right-hand side and simplify this, but I can see the link. So if you can't see the link, if you're like, I don't know how I'm going to make that look like this, then you might have to get this and simplify it a bit. So you go right-hand side and then simplify it. But I can see the link. And I hope you can as well, because it's a fairly simple link in this case. K plus 1 times k plus 1 plus 1. There's 2 is 1 plus 1. And this is equal to the right-hand side, QED. This is where you can use QED, not in a math methods paper that doesn't involve proof. So QED, we have proven that it works for k plus 1, given it works for k. So I've now shown that if I knock down a domino anywhere in that infinite trail of dominoes, the next one is guaranteed to fall down. And therefore, if I knock down the first, it will knock down the second will knock down the third, etc., etc. So my last statement here is conclude, and I say, therefore, if it, oh no, well, let's change that. If is a little bit incorrect. So it works for n equals 1, and therefore it works for n equals 2. And it works for n equals 2, and therefore it works for n equals 3, and so on. And we're done. That's it. So your concluding statement here needs to be something. You have to make a conclusion about it, and that conclusion should have some sort of implication that if it works for 1, it will work for 2. If it works for 2, it'll work for 3, and we've proven it works for 1. And therefore, it'll work infinitely. At this stage, I don't quite know what their mark allocations will be for that, but middle of the year, we're going to get, I'll get access to 2 practice external exam papers, and they will have a proof by induction in them. And so I'll get a chance to have a look at their mark scheme for that, and I'll be able to come back to you on that. But I'd probably say there's going to be a mark allocated for something substantial there. But what I'm going to do is I'm going to do lots of examples. I'm probably get a bit lazy with that. You have to make sure in your exams that you are providing that conclusion. Okay? Any questions on that? So that is considered abstract. It's considered quite complex, but realistically it's a fairly easy procedure to master. And the only thing that really gets complex in it is some of the questions you get some more complex algebra to deal with. This is a pretty easy example. My second example, I think, provides a bit more complex algebra.
So would this be considered complex for me later?
This one might be considered simple for me because it's pretty simple. But most of them will be complex for me, I'd imagine.
Is the proving equivalence statement the lesson I missed?
Maybe. I filmed it.
Yeah.
We may have all said hello to you on the video.
Maybe.
No, we didn't. Okay, second example. I'm actually going to give you some time, and then I'll record that separately. So it is actually quite similar and probably quite doable. So there's the second example. Prove that 5 plus 9 plus 13 plus ... plus 4n plus 1 equals n times 2n plus 3 for all n greater than 1 existing in the natural numbers. I'll give you how long? Remember your negotiation skills here?
10 minutes.
10's a long time.
7.
Let's go 5. Let's go 5.